mainly discussed about the phenomena of magnetization, and we said that for matter material, we think that they contain many tiny magnetic dipoles. Okay, and there are two mechanisms that I discussed so far. One is this paramagnetism. Is really these dipoles are really associated with the spins of these unpaired electrons. Okay, so once they are put into the magnetic field, they experience a torque that tending to line these dipoles up parallel to the external magnetic field, thus make the field increase. Then the second one is really the diamagnetism. So this one is mainly due to the contribution of these orbital circuits, where the electrons move around the nucleus. Okay, and what happens is once the magnetic field is applied, this electron this orbital speed of these electrons, is changed. Either speeds up or slow down depending on the direction of the magnetic field. And what happened is it will change, the speed changed, and thus the dipole moments changed. And the way it changed is it will change this orbital dipole moment in a direction that is opposite to the direction of the magnetic field. Okay, so these are really just the two mechanisms that we discussed for material magnetization. So in other words, that we can define a, a, a vector called magnetization, which is really indicate what is the amount of magnetic dipole moment per unit volume. Okay, for a normal material, because even though there are many tiny dipole moments there, but because of the thermal collisions, they are aligned in different directions. So on average, this m is equals to 0. It's only when the magnetic field are applied, and these dipoles tend to align toward the field or opposite to the field, and thus you can have a net magnetic dipole moment per unit volume. And you remember that this is very similar to the polarization vectors that we defined before. Okay, so it's really the kind of the electric dipole moment, okay, per unit volume. And when we have electric field applied, and the nucleus and the electron cloud tends to have some separation and create this tiny electric dipole. And if you have magnetic field applied, these dipoles will tend to move along line up with the electric field direction, and then create this polarization. Okay, so you can see that these two concepts are very similar to each other. And the magnetic field magnetization effects are often small and often hard to observe. Okay, this is mainly because of the mu zero value is much smaller than this 1 over epsilon 0 for the electric case. Okay, so this is how we talk about magnetization. Now, once we have that, of course, we have an object that is magnetized, and we want to figure out what is the field, magnetic field. Okay, the field of a magnetized object Okay, so now let us say I have some material. Okay, and there are some magnetization. Okay, M here. Okay, that it can depends on the positions. Okay, we wanted to know what is the magnetic field for this point in question. Okay, so what we do is like what we did it before. We can have a polarized object. We wanted to figure out what is the electric field here. So the way to do it is for the electric case, we divided to this tiny dipole, electric dipoles. Okay, and then we use the equation to calculate the potential. Okay, and then we do exactly the same thing. We divided things to very small area, volume. Okay, and when we can treat each one as a small magnetic dipole. Okay, and this is the volume is d tau prime, and the dipole moment is m, and the distance between these, let us assume, is the cursive r direction. Okay, so now for this, we have the formula that we described before. Okay, look at the dipole, magnetic dipole, and how to figure out the A there. So what is really is just mu zero divided by 4 pi is this magnetic dipole times the direction divided by the direction square, the separation vector distance square. Okay, so now we have the whole area. Okay, so this is just for one magnetic dipole. Okay, how to figure out the vector potential. Okay, now of course we have this whole object. Okay, we just need to do the integration. Okay, so this is m. Okay, this is okay, and we need to times the d tau. Okay, because that tells us what is the magnetic dipole, for that small volume. Okay, when times height divided by cursive r square. Okay, so this is what we have. Okay, then we do exactly the same thing, like what we did before for the when we calculate the field for polarized objects. We also use this relation. Okay, so we do the derivative with respect to the r prime variable for 1 over this cursive r. So this one will be cursive r square. Okay, so this is the formula that we have. So now we just replace this, okay, with this derivative. Okay, so this ar will becomes mu 0 divided by 4 pi. Okay, so this is becomes m r prime. We times this derivative 1 over cursive r. Okay, d tau prime. Okay, now what we do is we need to use also integrating by parts. Okay, so this is also very similar to what we did before. Okay, so I just write down the formula, and you will see that it becomes two components now. Okay, so m r d tau prime. Okay, one is this component, and then there is a second component, is this. Okay, so now there are two terms here. Okay, so what do you see from this term? Okay, this one is really looks like this is the potential of a volume current. What we call the JB, okay, is del cross M, okay. I mean they're both reserved to prime variable. Now I just switch everything to R, okay, so it will be easier, okay. So now this formula is really the potential of a volume current that look like this, okay. So this formula is really the potential of a surface current. Okay, I use KB to indicate this. Okay, M cross N hat. Okay, where is N hat? This is the normal unit vector direction. Okay, so it looks like this. Okay, so in other words, that for this magnetized object, okay, we calculate the vector potential. What we do is we kind of treat it as two pieces. Okay, one is, there is some object with some volume current. Okay, then there is another effect. You can treat it as the same object, but now it has a surface current. Okay, what you need to do is you calculate the potential for this volume current, you calculate the potential for this surface current, and then you add them together and you get the vector potential of this magnetized object. Okay, so I think you should know it very well. So this is really, I put a B there, indicate this is what we call the bound current. Bound currents. Okay, you remember that for the electrical case, that the field of a polarized object really is the same as that of a bound volume charge. Okay, there is a volume charge. Okay, and a bound surface charge. Okay, so in other words, that when we talk about electrical field in matter, we said the vector the scalar potential is really equivalent to the to the same object, but now we consider a bound volume charge written this way, plus the field that is caused by surface charge that is defined this way. Okay, so similarly for the magnetized object, okay, the potential is equivalent to the potential of a volume current, okay, which is we call the bound volume current, okay, that is written this way, and the potential of a bound surface current, okay, that is written this way. And you can also see that the formulas are very similar to each other. Okay, now let us just show you the example. Let us consider, so when we talk about polarized object, we consider a uniformly polarized sphere, and we need to figure out what is the electric field around it. And the same thing, let us say I have a uniformly magnetized sphere. Okay, I wanted to figure out what is the electric field around it. Okay, so the way to do it is really, let us say we have XYZ position. Okay, let's say this magnetization vector is m for this object here. Okay, and now we wanted to have a position r. So we wanted to figure out that this is a phi if we use a spherical coordinate system. And we found what we wanted to figure out what is the magnetic field here. Okay, to do that, as I showing here, to calculate the vector potential, you just need to calculate the vector potential for this bound volume current. Okay, then you calculate the potential for this bound surface current. Okay, then you add them together. Okay, so what we do is we first calculate the bound volume current, okay, which is defined del cross m. And because this is uniformly magnetized, okay, so this one becomes 0. Okay, so then we need to calculate what is the bound surface current. Okay, so this is m cross n hat. Okay, where n hat is of course is the direction that are pointing afterward. Okay, m is along the z direction, so we should really be m sin theta. Okay, that is the direction becomes along the phi hat direction. Okay, so now you can see that so this magnetized object, the vector potential will be equals to the vector potential of these two added together. And since this is 0, so what we really care about that is really we only need to care about this surface bound surface current. Okay, so if you remember that we discussed before, if we have a uniform surface charge, so if we have a sphere, okay, that have uniform surface charge on it, if we rotate it, not is really a spherical shell. Okay, spherical shell. Okay, it's not a sphere, it's a shell. Okay, that has uniformly surface charge, that is doing rotate along its axis. Okay, so if you look at the examples that I showed before, so this one corresponding to a surface charge, surface current. Okay, that has a surface current density which is the surface charge times the velocity. Okay, velocity is really omega r times sin theta along the phi direction. Okay, so what do you see that? You see that if we treat these whole things as m. Okay, so now you see that this magnetized object vector potential is equals to the vector potential that are caused by this surface current. And we said that if we have a spherical shell, if it's doing rotation, okay, and then the surface current will look like this. Okay, so in other words, that the field of a uniformly magnetized sphere is actually identical to the field of a spinning spherical shell. Okay, and what you really need to do is you just replace that sigma times omega r as the m value that are showing here. Okay, so now you can look at the example that I also described before. If this is example 511. Okay, so there we already calculated. Okay, go look at this, and we already calculated the magnetic field. Okay, inside the sphere. Okay, this is inside. Okay, will be just look like this. Okay, look at what I described before. Okay, And then the field outside, okay, is really outside is really just is the same as that same as the field, same as a dipole, magnetic dipole. Okay, and that magnetic dipole is just really calculated, is really the volume of this sphere times the magnetization per unit volume. So in other words, this really indicate what is the overall magnetization of this sphere. Okay, so you can see that you know is this example seems to be complicated, but after you consider of this, okay, it is pretty straightforward, and we can use the information that we described before for a rotating, spinning spherical shell with a uniform surface charge. Okay, you can use that knowledge to figure out the magnetic field. Okay, for a uniformly magnetized sphere. Okay. Okay. Now, of course, like what we described before for the polarization, we said there are tiny electric dipoles. They connected to each other. The two neighbors they cancel with each other. So you really have a long electric dipole, that are on the surface, and then also we talk about to create the volume charge. Okay. So now you may say, okay, what is the physical interpretation of these bound currents? Okay, why there are volume currents? Why there are surface currents? Okay, so what do we do is really, we can just quickly explain, how it looks like. So let us consider material. Let us consider a very small, a thin slab that is uniformly magnetized. Okay, so now we have very small, tiny, okay, tiny current loops. Let us consider the rectangular shapes. So what do you see that? Okay, so we have this. So what do you see that is really all these internal currents? Okay, one goes this way, then the other one goes the opposite way. So all these internal currents, they will cancel. So at the end, only the edge, okay, because around the edge there is no adjacent loop, to do the canceling. Okay, so then you can think about that, the whole things, at the end for this slab, you can think about that is really at the end is really a current, okay, a single ribbon of current I that are flowing around the boundary. Okay, if you think about that, okay, it's each one is a tiny thin slab of this polarized dipole moments. Okay, and then all the internal currents they cancel. Then you only are left with the currents that are on the edge. Okay, so the whole thing looks like a ribbon. Okay, with the current flowing around the boundary. Okay, now let us assume each one of them is really, as I said, it is a small square here, and it has some thickness. Okay, that is T. Let us say the area is A. Okay, so we have the overall magnetization. Okay, so let us only for this small one. Okay, the magnetization, of course, this is the magnetization times the volume. Okay, because this is defined as per unit volume. So this is really the area times the height. Okay, and we also we can treat it as a dipole. Okay, the dipole is really the current times the area. Okay, so if we kind of treat these whole things, as m. Okay, so it just look like this. So in other words, this I will be m times the t. Okay. Okay. So once we have the current, okay, is moving this way, and the length, the thickness is t. Okay. So here is really the thickness. Let us say assume is t. So now we have this surface current. Okay. Really just be this I divided by t. Okay. So in other words, that this is really m. Okay. So the magnitude of this surface current is basically m. Okay. Is really the value of this magnetization. Okay. However, the direction, okay, you will be able to figure out is really m cross this n hat. Okay. M is this way. Okay, the direction, if it's on the surface, is pointing outside, so m cross n hat will give us the direction of this surface current. Okay, now you can see that here is this is what we derived here. Okay, so you can see that this kind of a very simple picture tells us what is the physical interpretation of this surface, this bound surface current. Okay, you see it's pretty cool. Okay, now the same thing is we can also do that for the when this magnetization is non-uniform. Okay, for that you have to consider two volumes. Okay, because the B field can be different. The B field value here and the B field value here are different. Okay, so in that case, so here we assumed the neighboring loops they will cancel. For this case, that because the B field is different, then the current will not cancel. Okay, so the two adjacent of these chunks of this magnetized material will not the surface where they join. Okay, the currents will not cancel with each other, and there will be a late current. And you can calculate along the x direction and along the y direction. Okay, so I will not be able to really do that for you, but at the end you will find that the current, okay, will just look like that. Okay, so you can look at my lecture note or look at the Griffin's book. Okay, so this one tells you, this is what is the meaning of this. No, it's not magnetic field. It is the magnetization. Okay, value. For this small chunk and this big chunk, they are different. Okay. So this is because of this. Okay, so there are surface current, that are near this surface where they join, will not cancel each other. Okay, that created kind of the volume, the bound volume current. Okay, which is calculated with del cross m. Okay, so this is just to show you how we do the calculation. Okay. So now once we have this, okay, you see that now if we have an object there, we apply the magnetic field, and now the object will becomes magnetized. Okay, so you will have contributions from this bound volume current and also from this bound surface current. Okay, so of course they will change the magnetic field. Okay. So now, like what we have for the polarized objects, we have applied electric field, and then it will cause the bound surface charge, and also create this bound volume charge, and they will change the electric field. So then the same thing we will do it here. So we'll like what we did for we introduced the electric displacement to include the polarization effect. So now we also create another variable called auxiliary field. Okay, we call it H. Okay. Okay. Now what do we do? Like what we did before. Okay. So we want to write down this Ampere's law, for this magnetized material. Okay. But because it's very hard to really control the bound currents, include bound volume current and also bound surface current. Okay, so we have JB del cross M, we have KB, that is M cross N. Okay, so we have this bound current, and we also have some free currents, the other things that we can apply. Okay, so the total current will just be J equals to the bound current plus the kind of the free current. Okay. Okay. So this is the effect that is due to magnetization. Okay. If you remember what we did it for the charge, we also have equals equals to rho bound charge plus the free charge. Okay, the surface current and surface charge will not show up because you can, as I described before, you can treat it as a very tiny thickness, along the surface, where this one changes dramatically. Okay, to zero, the volume current. Okay, so we don't really need to worry about the surface current. Okay, so now we have this. Okay, so now remember that the Ampere's law is really this one is mu 0 j, let us divided by mu 0. Okay, so this is what we have for the Ampere's law. Okay, now this J of course include the magnetization and also include the free current. Okay, they are both effects there. So this is just del cross M plus JF. Okay, now we want to move this to the other side. Okay, so we really have this B divided by mu 0 minus M equals to JF. Okay, the reason we wanted to do this because these are free current. We can often easily control it. Bound currents, they are often difficult to really for us to control. When we apply some magnetic field, whatever magnetization for that object, they will form it. Okay. So this is what we have. Okay, so this is kind of the Ampere's law, but written in presence of the magnetized object. Now, if we define this whole thing as H, okay, H is B divided by mu 0 minus M. Okay, so what we have is del cross H now equals to JF now. This is the current. Okay. Of course, we can also write it down in this integral format. Okay, so this is really in kind of F. So this is really the total current. okay, that are enclosed in this what do we call that, Amperian's loop. Okay, we create a loop. Okay, we try to figure out how much is the total free current passing through that loop. Okay, okay, so you can see that the what do we have that this is very similar, okay, to the electric displacement current. Okay, electric displacement that we introduced before. Okay, uh, because we introduced that because we wanted to write down this Gauss's law in terms of just free charges. And here we introduce this variable, okay, because we just want to write down this Ampere's law just in terms of the free currents. Okay, we can ignore all the bound currents, we can ignore these bound charges because they are often not easy to figure out. Okay. Okay, so this is what we have. Okay, so once we have this, we can really we try use a simple case, okay, to use this this new Ampere's law, okay, for a magnetized object. So now let us think of this example. Okay, so now I have a copper rod. Okay, so a long copper rod. Okay, and it has a radius that is r, and there is a current I that are flowing through it. Okay, now we want to figure out what is the H value. Okay, this auxiliary field that is inside and also outside this rod. Okay, so what happened is we consider this copper. Copper is really a weakly diamagnetic. So this is really weakly diamagnetic material. Okay, so in other words, it will create some magnetization that has directions that is anti-parallel, to the current direction. Okay, the magnetic field direction. You can think about that. Okay, so now what do we do is, we can look at we define a Amperian loop. Okay, that is inside. Okay, so what we do is the loop we have H dot dl equals to the I, the free current that are included. Okay, for the first case inside. Okay, what we expect H to be the same. Okay, so H because of the symmetries. Okay, so if let us assume his radius is S, H times 2 pi S, okay, that is the length, equals the current. Okay, so the overall current, okay, is I. Okay, if we consider this is the whole rod, so the current per area, okay, per unit area is I divided by pi r square. And now this Amperian loop has an area that is pi s square. Okay, so this is what we have. Okay, from here, we can really find that the H, okay, is really I divided by 2 pi r square times S, and you can find the direction is really, the phi hat direction. Okay, so this is the inside, where S is less than R. Okay, now consider outside. Okay, outside we just create a loop. Okay, so H times 2 pi S is still the same. But now what is the total current that is inside this loop. Okay, for this you can easily see it's just I. Okay, it's just I. Okay, so from here you can see that H is really just I divided by 2 pi s phi hat. Okay, this is the case for s is greater than r. Okay. Okay, and then of course outside. Okay, for this outside, m is really 0. Okay, there are no copper outside. Okay, so then b is just mu 0 h. Okay, which is mu 0 I divided by 2 pi s phi hat. Okay, and of course, we can also calculate the b inside, but we needed to know what is the m distribution. Okay, currently I didn't provide you that information, so that's why you cannot do the calculation right now. Okay, so once we have this, of course, like what we did for the magnetic field, like for the electric field, we also needed to consider the boundary conditions. Okay, so this is very similar to what we had before. You remember previously we have the magnetic, if there are a surface that have current, okay, then the B field above and below that surface for the component that is perpendicular to the surface, they are really continuous. Okay, so we have this one equals to 0, and for the parallel one, the B field parallel to the surface equals to mu 0 k cross n. Okay, where k is just the surface current. Okay, now if we have the material, okay, that is magnetized. Okay, so we just need to change, we need to consider that effect. So h above minus h below for this perpendicular direction, we are just equals to minus m above, okay, minus m below. Okay, also for this perpendicular component. Okay, then h above for parallel direction. Okay, so because it's a surface, it has 2 directions, so that is why I put a vector there. So this is below. Okay, so this is really just equals to kf cross n hat. Okay, whereas this kf is really just the free current, free surface current. Okay, the formula here, of course, include both free surface current and also the bound surface current. Okay.